This conference will now be recorded.
Hello everyone. Today's topics will be natural rubbers. After that, vulcanization of rubber, synthetic rubber, copolymerization, and biodegradable polymers, and related problems. Natural rubber. So, as the name suggests, they are naturally available. Okay. So here you can see the picture. It is how it is obtained. It is obtained from the latex that excludes from cuts in the bark of the rubber tree, which is clear from this picture. And the polymer structure, as we can see here, only carbon and hydrogen, these two atoms are present. So this is a kind of hydrocarbon. CC double bonds are also present. Now these CC double bonds, they are Cs in nature. If you just focus only on one CC double bond, and on left hand side carbon there is hydrogen and this large group. Right hand side carbon we have methyl group and again this large group. So in both carbon, the large groups, they are on the same side. So this is the large group, this is the large group, this is small, this is small. So as smaller groups are on the same side and larger groups, they are on the same side. So this is cis, and the name is cis 1,4 polyisoprene. So as in the name you can see poly and then isoprene, that means the unit monomer unit, the name will be isoprene. Okay, you will also see the structure of isoprene. So the monomer unit, it is isoprene, but if you want to know what is IUPAC nomenclature, it is 2-methyl buta 1,3-diene, or you can also call it 2-methyl 1,3-butadiene. Both are actually correct. So it will be 4 carbon chain at 1 and 3 position. There will be double bond. So this is carbon number 1, this is 2, this is 3, and this is 4. So at carbon number 1 and carbon number 3, there are double bonds present. So that is why it is 1,3-butadiene or buta 1,3-diene. And 2 position there is methyl groups also. And that is why the name, IUPAC name will be 2-methyl buta 1,3-diene. But mostly it is known as isoprene. And the polymer is natural rubber. So the structure of natural rubber that you are seeing here, this is the repeating unit which is within the third bracket. Okay, and the first picture that you have seen here, the repeating unit that are shown 4 times, 1, 2, 3, and 4. But actually if you see in the repeating unit, as in the monomer unit, there are total 5 carbons, right? In the linear chain 4 carbon, and in the methyl there is 1 carbon. So it is 1 plus 4. Total number of carbon is 5. So obviously in the repeating unit 5 carbons will be present. Okay. So if I mark the repeating unit, it will be like this. So let me use it and write it properly. 1, 2, 3, 4, 5. So this is the repeating unit which is coming again and again. So in this way you can recognize when a polymer structure is given, and if you know what is the monomer, you can easily understand the the repeating portion. Because if you understand this clearly, then only you can answer some questions. Okay, because sometimes some structure will be given in the options and you have to choose which is the correct polymer structure. Suppose a monomer is given and the correct polymer structure you have to find. So once you know the monomer structure, you should recognize what is the polymer structure. So remember, the basic rule is in the monomer structure, if there are n number of carbon, so in the repeating unit of the polymer, there should be n number of carbon on it. Fine. Some more information. Natural rubber, it is not so strong or elastic. Now, as it is only carbon and hydrogen, I mean it is hydrocarbon, there is no electronegative groups present like oxygen, nitrogen. These are not present. No polar groups are present like NH2OH. So you can expect dipole-dipole type of interaction, that is any polarity generation, that is not possible in this molecule because it is simply hydrocarbon. And also there is no electronegative group. You cannot expect any positive charge or negative charge. So that is why electrostatic interaction, dipole interaction, all this it is not possible. So only very weak intermolecular interaction can be present, weak van der Waals interaction, and because of that it is not very strong, it is not also very elastic. Now at higher temperature, now when I'm saying high temperature, it means greater than 335 Kelvin, it becomes soft. And if the temperature is below 283 Kelvin, then it becomes brittle. That means only in the temperature range starting from 283 up to 335, it is okay. Otherwise, if you increase the temperature beyond 335 or decrease the temperature beyond 283 Kelvin, there will be some problem. Okay. It is attacked by oxidizing agents and also some organic solvent. So these are some of the problems that we can face with natural rubber. Now to overcome all these problems, we can have vulcanization of rubber. So what it means, as natural rubber we cannot use very extensively for commercial purposes because of the problems that are mentioned already in the previous slide. So what we can do, the properties of natural rubber we can modify by the process vulcanization. So in this process what we do, we make some sulfur-sulfur linkage between two adjacent chains and it limit the motion of the chains relative to each other. Okay, so suppose there are some chains individual and you are making some sulfur-sulfur linkage between these two chains, and as a result now there will be some comparatively more strength will be there compared to the previous structure. Now this process of introducing sulfur-sulfur cross-link in the structure of natural rubber, how? By heating with sulfur, that is you just heat natural rubber with sulfur at a particular temperature 110 degrees centigrade, and that process is vulcanization of rubber. Now you can do this in two ways. If it is 1 to 3% sulfur, then the nature will be soft and stretchy. If it is 3 to 10% sulfur, that is amount of sulfur is now increased, now it will be harder but flexible. So here we have taken two chains of natural rubber, number 1, number 2. Now in between these two chains, when it is heated with sulfur at 110 degrees centigrade, you can see some sulfur-sulfur linkage is generated and the CC double bonds are now lost. So in this way, because of this type of structural change, because of this formation of cross-linking, now its properties will be different and now they will be suitable for commercial purposes. Because if it is only natural rubber, we cannot use it extensively for commercial purposes, but now we can do so after vulcanization. Once we know natural rubber and its modification, next topic is synthetic rubber. Polymerization of certain organic compounds. Which compounds? Buta-1,3-diene or 1,3-butadiene. This is the structure, 4 carbon chain, 1 position double bond, 3 position double bond. This is the structure of buta-1,3-diene. Or you can take some of its derivatives. Suppose in any position of carbon, if there are some groups present, so that will be derivative. So either buta-1,3-diene or its derivative, that will give us rubber-like polymer, and with desirable properties like stretching to a greater extent that we cannot do with natural rubber. But in synthetic rubber, that is man-made rubber, starting from this buta-1,3-diene or its derivative as a monomer, we can make this in the laboratory. So it is synthetic rubber. Now you can do so by two processes. You can do homopolymerization. That means only one type of monomer will be there. That is 1,3-butadiene derivative will be there only. You can also do copolymerization. Copolymerization means now two types of monomers will be there. So 1,3-butadiene or its derivatives, that is one fixed monomer that is always present, as we have seen in the first point as a definition of synthetic rubber, that will always be present. In the homopolymer, you have taken only this monomer, but now another unsaturated monomer. So the second monomer that you are taking, there will also be some unsaturation. So by both the processes, we can make synthetic rubbers. Now we will see preparation of some synthetic rubbers, examples, one by one. The first one is neoprene. Okay, don't be confused with the names because it may sound similar. In natural rubber, we have seen the name of the monomer unit is isoprene. Okay, so don't be confused between these two. Neoprene is the name of the final polymer. Here the monomer is, you can see this is the structure of monomer. So it is 1,3-butadiene, but not 1,3-butadiene directly. It is the chloro derivative. Which position? At 2 position. So it is 2-chloro-buta-1,3-diene, or you can also call it chloropene. You can also call it 2-chloro-1,3-butadiene. So this buta, whether you place it before 1,3 or after, it is fine. Both are correct. So number 1, 2, 3, 4. So at 2 position we have chloro substituent. So that is what is 2-chloro. Position of double bonds 1 and 3. So that is why the name 2-chloro-buta-1,3-diene, but it is mostly known as chloroprene. So the final polymer name is neoprene and the monomer unit is chloroprene. Now it is superior to rubber and resistant to chemical reaction. That is, compared to natural rubber, it is having some better property. It is used in the manufacture of chemical containers. So you can keep chemicals in this, that is any container made of this. Conveyor belt, hoses, that is hose pipes, etc. And here, as it is homopolymerization, because you have taken only one monomer, which is 2-chloro-buta-1,3-diene. So it is homopolymerization, example of homopolymerization. And it is free radical. We know polymerization, when it is addition polymerization, it can be free radical, anionic or cationic. So this is under the type free radical. This is the first example for synthetic rubber, number 1. Second one, Buna-N. Here we have taken 2 different monomer. Number 1 is 1,3-butadiene, which is you have to take according to the definition of synthetic rubber. You have to take 1,3-butadiene or any of its derivatives. This is number 2. So in the number 2 monomer also you can see the some unsaturation is present. This is known as acryl nitrile, or you can also say vinyl cyanide, because CC double bond, this group is known as vinyl group. It is prepared by copolymerization of acrylonitrile and 1,3-butadiene in presence of peroxide catalyst. Fine. It is resistant to action of petrol, lubricating oil and organic solvent, and uses making oil seals. That means as it is resistant to the action of oils, so obviously for oil seal you can use it, tank lining, etc. Now the next polymer that we are going to discuss, that is known as similar type of name, Buna-Ace. So how you will remember these two so that you are not confused? Just remember, in both cases the first monomer unit is common, that is same. Here also it is 1, this is also same. But the second one is styrene, which starts with S. In case of Buna-N, the second monomer is acrylonitrile. So try to remember N for nitrile and S for styrene. So now the monomer units are styrene and 1,3-butadiene. So in the repeating unit, there must be presence of this 4 carbon, which is coming from 1,3-butadiene, and this 2 carbon, which is coming from styrene. Similarly, if you look at the structure of Buna-N, the 4 carbon that is coming from butadiene, now the position of double bonds are changed. It is not in the same place. And the 3 carbon that is coming from acrylonitrile. So this is the repeating unit. As I have said, in the repeating unit, the total number of atoms that are already present in monomer, it will be same as you can see here. So it is the source of 4 carbon, it is the source of 2 carbon. So you can also see it here. This is 4 carbon up to this, and then these are 2 carbon. Okay, so total number of repeating unit will be 6, and Cn is the substituent. Now in presence of sodium metal as catalyst. Fine. So this is Buna-Ace. Now question regarding this, vulcanization of rubber is carried out by heating a mixture of, remember, natural rubber we start from isoprene, and sorry, actually it is natural rubber, so only to know what is the monomer, that is enough, because we don't synthesize. But when it is vulcanization of rubber, we introduce some sulfur-sulfur linkage. So obviously when you are heating this mixture, there one part must be sulfur. So these two you can easily cancel, because in these two options there is no mention of sulfur. Only these two options there is mention of sulfur. So either B or C will be correct. Now among these two options, B and C, neoprene and sulfur, this is not correct. Why? Because neoprene is the name of one of the synthetic polymer. First of all, it is synthetic polymer. It is not even monomer. It is a name of polymer. So it cannot be correct. So correct is isoprene, because the monomer unit, remember the structure of natural rubber, the monomer unit is isoprene, 2-methyl-1,3-butadiene. That is isoprene. So the monomer unit of natural rubber, when you heat it, it's not simple heat. You are heating it in presence of sulfur. Then only sulfur-sulfur linkage is possible. Okay, so that is why option C will be the correct option. In the polymer Bunais, A stands for what? Sulfonation. We have not done any sulfonation. In the previous slide, we have just seen the preparation method of Bunais. So we are not doing any sulfonation. It is not for strength. It is not for sulfur, because there is no mention of sulfur. But styrene is there. So this should be the correct option. Which one of the following polymers is not obtained by condensation polymerization? So we have to understand what is condensation polymerization. Mainly two methods we know. One is addition polymerization, and by the mechanism free radical mainly, and another examples are also there, cationic anionic. Another one is condensation polymerization, where what happens, small molecules are removed. It may be ammonia, it may be alcohol, it may be water, anything. Okay, so any small molecule must be removed. Now one by one, if we look at the structure, we have to find that polymer which we are not making by condensation. Bunaene, that is the first option. So bunaene we have just seen. Here we heat 1,3-butadiene and CH2 double bond CHCl, vinyl nitrate. Okay, so that means two monomer units we have taken. It is obviously copolymerization, but we are not, that is, in this polymerization there is no removal of small molecule. There is double bond present in the monomer 1, also double bond present in the monomer 2. Okay, and in the polymer there are some new double bonds formed, but there is no removal of small molecules. So that is why this should be the correct option. But if you look at the structure of other options, bakelite, nylon 6, nylon 6,6. So bakelite, in the last class we have seen its synthesis. We start from phenol and formaldehyde, and there are several steps. So in this case, CH2OH is present first, and CH2OH of one phenol ring, and the hydrogen atom from the other phenol ring. There is removal of this water molecule. So here removal of water molecule is involved. So this is condensation. Then if you look at the structure of nylon 6 and 6,6, amide bonds are present. So when amide bonds are present, after CO basically there is NH, which is clear from the repeating unit. Similarly in the left hand side, after NH there is CO. So amide linkage is, its formation is possible only when in one monomer unit there must be NH2, another monomer unit there must be CO2H group present. Rest of the part I am not writing, that is not important. We are just focusing on the groups which are actually involved in the reaction. So in this case, one hydrogen atom and this OH is removed in the form of water, and as a result you get NHCO bond, which is amide. NHCO. So here also removal of small molecule is involved. So obviously these three are not example of, these three are actually example of condensation polymerization. But if you look at the synthesis of bunaene, which we have just seen, vinyl cyanide or acrylic nitrile, here we have CC double bonds. In 1,3-butadiene also we have some CC double bonds. But the newly generated double bonds, now the position is changed. This is the position where the newly generated double bond is now present, and this double bond is also not here. So it is actually through free radical. generation. It is not through the mechanism of any small molecule removal. So that is why the Buna N, that option should be the correct option. So these are the examples for synthetic rubbers. Copolymerization, though we have used this term, but still we will discuss it separately. Copolymer, when you make starting from monomers, the process is actually copolymerization. The final product you get known as copolymer. So copolymer, this term we have just used in the previous slides. So in the copolymer, the starting materials, there must be more than one monomer. Fine. So the process of forming polymers from two or more. So at least two types of monomers must be there. And it may be more than that also. So two or more different monomeric units must be present. Then only it is copolymerization. Now copolymerization, you can do it both addition or condensation, because we know two types of mechanisms are there, addition and condensation. In condensation, small molecule is removed. In addition, there is change in the position of the double CC double bonds. But under that is both this you can apply for copolymerization. And as an example, formation of Bunaes we have just seen. Starting materials we have taken 1,3-butadiene having double bonds. Styrene, there is also presence of double bond. This is the first example which is under addition polymerization, as you can see here. Fine. So this is styrene, CC double bonds, then PH3 and 1,3-butadiene. Here no small molecule is removed. But this is copolymerization because you have taken two different types of monomer. Monomer number 1, M1, monomer number 2, M2. So this is under copolymerization, but it is addition. Another example is formation of nylon 6,6 starting from hexamethylene diamine, which is monomer 1. Another monomer is adipic acid, which is monomer 2. Okay. So this example is this one, hexamethylene M1, M2, and here NH2 group both side, CO2H group both side. So CO2H group, it will react with amine. There will be removal of water molecules. So you can see n number of water molecules are removed, and there will be formation of some amide group, NHC. Now copolymers, their properties are quite different from the homopolymers. Okay. Biodegradable polymers. So from the name we can understand these polymers, for these polymers biodegradation is possible. Materials that are readily decomposed by microorganisms, bacteria, virus present in the environment, they will be called biodegradable. So here natural decomposition, maybe it can take some time depending on the structure, but it is possible to decompose naturally. That is the definition. And by what? By microorganisms. So natural polymers, we know there are different types of classification we have seen in the first class, and one of these classification is based on source, whether it is natural or synthetic or semi-synthetic. So natural polymer means it is naturally available. So for those polymers, they can degrade on their own after a certain period of time. But for synthetic polymers, most of them are non-biodegradable. Natural decomposition is not possible. So synthetic polymers are very difficult to dispose of the polymeric waste. For example, polythene bag, leading to serious environmental pollution. So to get rid of this problem, what we can do, we can produce some biodegradable polymers. Now these biodegradable polymers, now natural decomposition is possible by soil microorganism, or it may be by enzyme catalyzed reaction within a reasonable period. That is enzyme catalysis, it is possible in vivo, inside the body. So as a result, biodegradable polymers and their degraded products, there will be minimal environmental impact. Okay. So if we want to know that why they are behaving in this way, because they contain similar type of functional group as present in biopolymer. Okay, so polymers is in vivo, they are known as biopolymers. Examples we have seen in the chapter biomolecules. Fine. So similar types of groups are present. Biodegradable polymers, if we want to know their application, they are mainly used in medical field. So some names are given here, and these polymers are decomposed by enzyme action and are either metabolized or excreted from the body. So suppose sometimes it is also present in controlled drug delivery, that means the drug that we are taking, I mean medicine, it is now it is present inside the body. Okay, so they can be decomposed by the enzyme that are present in vivo, or it can be metabolized, or if it is not possible, then it will be removed from the body naturally. So these are biodegradable polymers. Some examples here, we have total example 1 2 3 4 5 6, but out of this only these two we will focus. Fine. So the first name, poly beta hydroxybutyrate, CO beta hydroxyvalidate. So what it will be synthesized starting from two different monomer. So the first monomer will contain 4 carbon, so that is why it is butyrate. Second monomer is containing 5 carbon. In short, we can call it PHBV. So preparation of this PHBV, you can see this is the first monomer, 3-hydroxybutanoic acid. There are groups present OH and CO2H, 1, 2, 3, 4. At 3 position there is OH group, so that is why the name, IUPAC name, 3-hydroxybutanoic acid. And look at the second structure, it is almost same, only difference is 1, 2, 3, 4, now 1 carbon extra. So it is still 3-hydroxy, but now it is pentanoic acid. So the term validate, it is actually used for 5 carbon. Fine. And as there is presence of CO2H group and also OH group, that means alcohol. So between these two groups, what type of linkage is possible? Obviously ester. So it is polyester. Example of polyester. OH group, CO2H group together, it will make ester linkage. Okay, so both sides also you can find ester linkage. And total number of carbon, as we have seen here, total 4 carbon and 5 carbon. So 4 carbon is present in this portion, and in this portion 5 carbon present. Okay, so these are the two monomer units. The two monomer units are joined together by ester linkage. So this is polyester, used in orthopedic devices and in controlled release of drug. So this application you have already seen in the previous slide. PHBV undergoes bacterial degradation in the environment. Fine. Here we have a question, which polymer has chiral monomer or monomers? So it may be homopolymerization, in that case single monomer. It may be copolymerization, in that case two different monomer. Options we are having here, Buna N, nylon 66, neoprene, PHBV. So this is actually correct answer. You can understand easily, because if you look at the monomer units, here we have chiral center. So chiral center is basically this carbon, because here with this carbon 4 groups that are present, methyl group, OH group, H and CH2CO2. Similarly, this carbon is also chiral because 4 groups are different, ethyl group, OH group, H and CH2COOH. All the 4 are different. So in this case, both monomer, there is presence of chiral center. So suppose if you are sure about that in PHBV there is chiral center, you can easily choose this option. Even you don't have to look at the other options. Fine. And remember, neoprene, we have just seen is synthesis starting from chloroprene. So here basically no double bonds are actually present in monomer, but no chiral center present. Similarly, nylon 66 starting from adipic acid and diamino molecule. Okay, so here also we do not have any chiral center, and when it is Buna N, we start from 1,3-butadiene and acrylonitrile. They are also only double bonds are present, but no chiral center. That is carbon having 4 different groups, that is not present. So these 3 are not correct. The second biodegradable polymer is nylon to nylon 6. Remember, we have discussed nylon 6 and nylon 6,6, but this is something new we are seeing. Fine. In nylon 6, we use a monomer where both NH2 groups, CO2H groups are present. And when it is nylon 6,6, the monomers are 2 different monomers. In one monomer, there is NH2 group, another monomer, there is CO2H. Now, when it is biodegradable polymer, it is obtained by condensation polymerization of 2 monomers. One is glycine. Glycine is basically the simplest amino acid possible. Both NH2 groups, CO2H groups are present. And the second monomer is aminocaproic acid. So here monomers are, though they are having NH2CO2H, but it is different from nylon 6 and 6,6. Amide linkage, that means it is polyamide. Example. The previous PHBV, it is polyester. This one is polyamide. It is used in the bristles of toothbrush, strings of musical instruments, synthesis of artificial fibers. So this is a synthesis. Glycine, the first monomer, both NH2 groups, CO2H groups are present. Aminocaproic acid, both NH2 groups, CO2H groups are present. So the NH2 group of aminocaproic acid that can react with the CO2H group of glycine. Similarly, aminocaproic acid, its CO2H end, it can react with the NH2 end of glycine. So in this way it will continue. Fine. So this is the structure of nylon 2 and nylon 6. So in the repeating unit, obviously 5 carbon, this one total 6. So in this part you can see 6 carbon, and in glycine we have CH2 and CO2H. So this part is the repeating unit. And NH, this is the NH of glycine, this is the NH of aminocaproic acid. MCQ question. So this question is related to nylon 6, but this is multiple correct choice. So more than one option may be correct. So this biodegradable polymer, nylon to nylon 6, as we already know it is biodegradable. So this is obviously the correct option, right? Now is it copolymer? Yes, it is copolymer because you have taken 2 different monomer. This is the first monomer, this is the second monomer. So it is copolymer, it is not homopolymer, because if it is homopolymer, only one type of monomer is present. In this case, you have 2 different types of monomer. So that is why it is example of copolymer. So this is also correct. Come to the third one. Is it polyamide? Yes, it is polyamide because amide linkage is obtained, right? This is also correct. And obviously this is not correct because already we have selected biodegradable. So how it can be non-biodegradable? Okay. So as this chapter it is complete, as we have some time, we will discuss question related all the topics that we have seen in this chapter. Which of the following is an example of polyester? Butadiene styrene copolymer. So from the monomer name, you can easily understand there is no OH group or CO2H, because when I'm saying polyester, the presence of OH group and the presence of CO2H group must be there, because if you want to synthesize ester group, these two must be present. But when it is butadiene, only CC double bonds are present. When it is styrene, it is basically PH CC double bond. So there is no OH or CO2H. So this cannot be an example of polyester. Then melamine copolymer. So melamine polymer is basically one monomer is melamine, another one is formaldehyde. Now melamine having structure, it is like pyridine, but total 3 nitrogens are present and there is some NH2 group. So OH or CO2H group is not present, but NH2 group is present. And in melamine polymer, another partner is ACHO. So here aldehyde group is present, but not OH or CO2H. So this is also not correct. Then neoprene. Now neoprene, it is obtained from chloroprene, which is derivative of 1,3-butadiene. Here also we have only CC double bond. So see how neoprene is synthesized starting from 2-chloro-1,3-butadiene. We do not have any OH or CO2H. So this is not correct. Then melamine, this is the structure. There is NH2 group. It reacts with the formaldehyde, that means aldehyde group. So this is also not correct. But the last one is basically correct. Its synthesis we have just seen. It is example of polyester. So here we have CO2H group, OH group in both the unit. CO2H group of the first monomer, it will react with the OH of the second one. Okay. So this OH is basically this one, and this CO is basically this one. So see now this ethyl group, it is as if hanging as substituent. Okay. So this part is coming from 3-hydroxypentanoic acid, and the other part is coming from 3-hydroxybutanoic acid. Fine. So correct example is correct option is option D. Now for your convenience, here the heading is not correct. Basically here you can see some table where both polymer and monomer you can find simultaneously, because that is you can consider as if it is a list or table. So all the polymers that we have discussed in this chapter you can find simultaneously. Okay, so when you revise the chapter, I hope it will help you find. So polythene, polytetrafluoroethene, Teflon, then polyacrylonitrile. Though in some cases it is not that always you have to memorize it blankly. No, it is not that. Because see, when it is polythene, obviously the monomer is ethene, because the word poly is before ethene. When it is polytetrafluoroethene, so poly, just omit the word poly, remaining part is tetrafluoroethylene, so it will be the monomer, though sometimes it is mentioned as Teflon. Then polyacrylonitrile, that means acrylonitrile, that is the monomer, terylene or declon. Now two monomers are involved, so directly you cannot understand. It is glycol, 2 carbon, 2 OH, and terephthalic acid, benzene ring, 1 and 4 position, 2 CO2H. Nylon 6,6, here also two different monomers. In one monomer you have NH2 group, second monomer you have CO2H. Then nylon 6, single monomer, but both in two types of groups are present in the single monomer, NH2, CO2H. Novolac, it is actually the intermediate which you get before getting the final compound, which is bakelite. So Novolac is also polymer, and these are the monomer unit. This condensation polymer. Then we have phenol formaldehyde resin, which is nothing but bakelite. It is another way of saying bakelite. Starting material again same, because first Novolac is formed, then bakelite. So obviously starting materials will be same. Melamine polymers, melamine and formaldehyde. Bunaese, today's class we have seen its synthesis, styrene and butadiene. It is two monomers, both are having some CC double bonds. Natural rubber, 2-methyl-1,3-butadiene. Sometimes it is also called isoprene. Then the polymer neoprene, starting monomer is 2-chloro-1,3-butadiene. It is also known as chloroprene. Chloroprene monomer, neoprene polymer. Buna N, 1,3-butadiene. So it is same as Bunaese, only difference is the first monomer is same. Second monomer is styrene, here it is acrylonitrile. Then PHPB we have seen where it is has a specific property that the monomer is having some chiral center. Another biodegradable polymer, glycine and amino capronic acid. So as you have seen of these tables, it will help us to answer this question. So here we have to match polymer and monomer. Monomer in the right hand side column, polymer in the left hand side column. Now if you look at the options, always try to choose that, sorry, not try to choose, I'm trying to say, always try to find first that option where some uniqueness is there. What I mean by unique, see, in the first option you have B connected with 3, that you will not find in any of these options, right? Similarly, C is with 1. That also you will not find in any of these options. So whenever you are getting any of this type of option, just check that these two, which is unique, you will not get it in any other option. Whether these two you are sure or not. So B is related to 3. That means neoprene, its monomer is chloroprene. Look at the previous neoprene. Though here name is not given, but 2-chloro-1,3-butadiene is chloroprene. You can understand from the substitute chloropene. So B must be connected with 3. If you are not sure about it, just look at the other one. Is C connected with 1? So acrylonitrile. If you look at the previous table, here we have acrylan is basically this one. Another way of saying it, though it has some other names also. All the names I have properly mentioned when I have discussed it, probably in the last class, in previous class. This is the third class. In the second class, probably I have discussed. So polyacrylonitrile, you can call it acrylan. And when if it is directly mentioned as polyacrylonitrile, it is easy to recognize the monomer. But just see, there is some similar sounding acrylan. So C must be connected to 1, and B is 3. Yes. This is related to 3 because tetrafluoroethyl and teflon, fluorine is present in both. That is clear from the name. So this is related to this. Now in this way, we can understand if you are sure about these two. Suppose if it is not so, if you are not sure about this, it may be that you are sure about A2. So in that case, what you will do? You can maximum cancel option D. Now you are left between A, B, C. Now this part is common, so you have to look at the other part. But it will be better, suppose, if you are sure that, because these two are unique. So if you are confirm about it, you can easily choose the option. So here option A will be correct. A is related to 2, neoprene is related to chloroprene, and D is 4. Natural rubber monomer is isoprene, which is nothing but 2-methyl-1,3-butadiene. So this is the correct. Here monomer is given, which is CO2H, then some CH2 chain, and finally NH2. Now you have to find the polymer. But if you look at the reagents that are used, it is not that direct you are doing polymerization. First, there is a reagent which is NaNO2 in presence of acidic condition. Now, NaNO2 in presence of acidic condition, when there is primary amine present, what happens? There is diazonium ion formation. So, this NH2 group that will be converted to N2 plus. Now, as water is also present, because hydronium ion H3O plus is the hydronium ion, which is basically combination of water as well as H plus. That is actually hydronium. That means in the medium, water is also present. So this is not the final group. N2 plus that will be generated in presence of sodium nitrite. Now it will be converted to, that is hydrolyzed to OH group. So first this NH2 group will be converted to OH group. So don't think this is the direct monomer. You will get the monomer only after reaction with NaNO2 and H3O plus. So here the monomer structure is this one. This is the monomer. So in the monomer you have OH group, you have CO2H group. So obviously some ester linkage will be created both sides. Now if this is the monomer, obviously in the polymer structure nitrogen cannot be present. So these two you can easily cancel. Now you are stuck between option 1 and option 2, right? So how to understand the repeating unit? In this case, this H will be taking part in reaction, and in the CO2H side, OH will be taking part in reaction. That means in the repeating unit, there will be presence of carbonyl group and oxygen like this, and in between there will be total 1, 2, 3, 4 carbon chain. Okay. Now 4 carbon is present in both cases. But if you look carefully, in option 1, you have COO. Here you have only C double bond O, and this side is same for both. But as we have seen here, this OH is taking part, so it cannot remain in the repeating unit. Only that part will be in repeating unit which is intact. So that is why option 2 should be the correct option, not option 1. Next question. Homopolymer which is formed from 4-hydroxybutanoic acid. So first write the structure of 4-hydroxybutanoic acid. 4 carbon, and at 1 carbon there is CO2H group. 4 position there is OH group. This is number 1, this is number 2, this is number 3, this is number 4. So you can find some similarity with the previous, in the previous question also we have seen both side OH group and CO2H, and in between there are total 4 carbon. Here we have only 3 carbon, right? So if it is 3 carbon, that you can see in option 1 and option 4. That means 2 and 3 cannot be correct. Now in these two groups that are present both sides, this H is taking part and this OH is taking part. Remember how ester is formed. CO2H group and rest of the part not required, and HO group, rest of the part not required. So here what happens? This OH and H is removed. That means this CO intact, this oxygen intact. That means in the repeating unit, 3 carbon that must be present. One side there will be CO, then repetition. Another side there will be oxygen, then repetition. It should be like this. Okay. Now if it is so, and if you look at option 1 and 4, because 2 and 3 already not possible, that we have seen because of the carbon number that is not matching. So one side oxygen and another side CO, that you can find in option 4, right? So now you can see. So here directly the monomer structure is given, but structure is not given. Name is given, you have to draw the structure. In the previous case, there is some reagent. You apply that reagent, then you get monomer. But here monomer is given directly. So on one side there will be oxygen, another side there will be carbonyl, which is matching with this one. And these two you can cancel easily because here we have 2 CH2, which is not correct. We have total 3 CH2. Okay, and option 1 is not correct because in one side there is COO, but that is not repeating. CO is only repeating. Fine. Option 4 correct. Major product of the following reaction. Now this question is very interesting. Here 2 molecules are given, but remember the reagent given Et3N, which is base. Now base is used for what purpose, that you have to understand. Now forget about the options. You have to first write the monomer unit because you have been given 2 different reaction condition. It is not only free radical polymerization is given. Then you can consider as if it is the first monomer, this is the second monomer, but not. That is not the case. First, a reagent is given which is triethylamine, which is basically base. Obviously, some reaction will happen. Then you will get the monomer. Now, in this molecule, the first molecule, you have chlorine. Now, this chlorine is better leaving group compared to the other chlorine because it is COCl. Fine. Now this NH2 group, it will attack at this carbon, this Cl will be removed. It will not attack at the other carbon. Fine. That means NH2 group and Cl is removed and one of the hydrogen will also be removed. So it is basically the net removal of hydrochloric acid. Now acid is the byproduct which will be consumed by the base Et3N. That is the reason ET3N is used, which will help to remove the byproduct. As a result, according to Lee-Chatterjee principle, the equilibrium will be shifted from left to right. So that is the purpose why we are using ET3N. Now if you are thinking why not this NH2 is attacking, the reason is here the double bond lone pair is less available because it can take part in resonance with the carbon. So nucleophilicity of this NH2 group is less than the other NH2. So only this chlorine and this NH2 will be taking place in the will take part in reaction. So now we know why we are using ET3N and what is the first step. So see, this is the first step, and after generation this carbon and this NH, there will be bond formation. So this is the newly generated bond. Now this is your monomer. So you are having single monomer. This is the byproduct consumed by ET3N. Now you have to do free radical polymerization. Now as it is mentioned, free radical polymerization, it is not condensation. That means NH2 group will not taking part in reaction. Free radical polymerization means only CC double bond will take part. So this should be the actual reaction center. Rest of the part there is no change. So on one side of CC double bond there will be newly generated bond. Other side also there will be a new bond, and this CC double bond will be removed. Some other double bond, some other place will be generated. So if you continue only this CC double bond part, you will get this one. Now here it is already drawn, so it is convenient for us to understand. But simply by applying common sense, you can remove some options. How? Just look at the part which is intact. So the intact part, how it looks? CONH, CH2, CONH2. So you have to find in which option this intact group is present. CONH, CH2, CONH2. NHCO, CH2, NH2 is present, but this CO is not present here. Not correct. Same, see, it is not even correct because the ending part is CH2, NH2, but now it is COS, NH2. Not correct. Then CONH, CH2, CONH2. That CH2, CONH2. That also NHCO. Okay, we have cancelled option 2 already. Now if you look at option 3, what is the intact part? CONH, then Na again CO, then CH2NH2. But just look at the monomer which we have used. CONH, in between these two NHCO there is CH2, but that is not present here. So you are left with only option 4, where you have the same group which is intact. CO, then NH, then CH2, then CONH2. And only this part is repeating. Fine. So that is why it is within third bracket. So option 4 should be the correct option. Next question. Which of the following statements about low density polythene is false? Low density polythene, and we know two types of polythene, low density, high density. The first one, it is a poor conductor of electricity. Synthesis requires dioxygen or peroxide initiator as catalyst. That is to generate the odd electron, I mean the free radical. This must be present. Whether it is correct or not, that you have to understand. Used in the manufacture of bucket, dustbin, etc. Synthesis requires high pressure. So option B and D, these two are related to reaction condition. So we have to know all the information regarding the low density polythene, which is also, we write it like LDP. It is a bad conductor of electricity and chemically inert. So this is not correct. Sorry, this is correct. We have to find which one is not correct. That will be the correct option. So this is basically, better I write, it is true. It is synthesized through polymerization. So obviously here we have to use some initiator. This is correct. high pressure is required. Look at this value. This is very high. This is also correct, but use is different. Bucket dustbin, these are actually used with high density polythene, not with low density polythene. So that is why this is actually false and this is correct option. Okay. So flexible pipes, squeeze bottles, toys, all these you can understand from this material texture, their quality. It is obviously with low density, because when it is bucket dustbin, it must be very hard, which is not possible with LDP. So that is why it is not correct. The formation of which of the following polymers involves hydrolysis? We know two different ways we can do so: addition, polymerization, condensation, polymerization. But this is something new we are here. Actually, this is only unique for only a particular polymer. So when it is all these structures, as you can see, nylon 6,6 and nylon 6. Here, in case of nylon 6, is two different monomer you use. In one monomer, two amino groups are present. This part is coming from one monomer, this part is coming from another monomer. Through condensation, where water molecule is removed. When it is bakelite, then also water molecule is removed. When it is steriline, this part is coming from ethylene glycol, another part is coming from 1,4-dicarboxylic acid. I mean benzene, 1,4 position CO2H group. But when it is nylon 6, it is basically a single monomer having both NH2 group and CO2H group. So NH2 end will react with CO2H, CO2H end will react with another NH2. But remember, before the condensation step, there is another step, because we start from this type of cyclic amide, and when we do hydrolysis, then only you get the actual monomer, then it is removal of water, and that is condensation, polymerization, which is basically in step 2. But if you see step 1, it is obviously hydrolysis. So which of the polymers involve hydrolysis? It is option 4, nylon 6. So we're at the end of the time. Just one question, which is very easy to answer. Which of the following is a fully fluorinated polymer? PVC, okay, Teflon, thiocol, and neoprene. So PVC is having structure like this, polyvinyl chloride. So it is starting, and that is monomer should be like this. And neoprene, here the starting material, it is actually 1,3-butadiene having chloro substituent. The position of double bonds, now it is changed, but this is the basic unit. Thiocol, though we have not discussed it, but look at this structure, it is having sulfur heteroatom. Only Teflon, there is presence of fluorine. So it is fully fluorinated, because if it is a CH2 single bond CH2, the starting material is ethyl. But in this case, the starting material is F2C double bond CF. So it is fully fluorinated polymer. Okay, so that is why this is the correct option. So we are at the end of the session. Thank you for listening.